Welcome to the new generation of the ARTOS rover project, Kerberos. Kerberos is a Mars rover demonstrator developed by the ERIG of the Technical University Braunschweig. For this year's ERC edition, ERIG is collaborating with AKAMAV of the TU Braunschweig and TUC Drillbotics of the Clausthal University of Technology. The rover itself is built by Team ERIG. Their team is made up of 4 groups of members: Project Lead, Outreach and Money, the technical engineers, and all the technical consultants. The TUC Drillbotics team from Clausthal is split up into lead and engineers, while the drone team AKAMAV from TU Braunschweig is a collaboration of 3 engineers. Our goal is to share our passion for space technology and robotics with future generations of researchers. The ERC shares many of our ideals of technological progress, education through communication and teamwork, and also creates a melting pot of people and ideas from many backgrounds sharing a common passion. During the last years of participation in ERC, we learned many lessons regarding the limits of our current rover design, some of them the hard way. To overcome these problems, we realized that we needed a new generation of rover for this edition of the ERC. With ARTOS reaching its retirement, we introduced Kerberos as the young and fresh successor platform. During the design of Kerberos, we kept some of our favorite and most successful features of ARTOS and focused on improving the following main attributes: reliability, modularity, upgradability, and ergonomics. The new chassis, constructed from standardized aluminum frames, makes mounting current and future subsystems easier. Its modularity enables the easy replacement of parts, but also helps future-proofing the design by maintaining upgradability. The modular frame design also facilitates huge improvements to the ergonomics of working with Kerberos. Due to many issues with the highly integrated ARTOS control unit, or OCU, which placed all critical electronics interfaces on a single extremely complex PCB and made repairs and replacement time and cost intensive, we decided to improve reliability by breaking down the main electronics into smaller submodules and cleaning up our cable management to facilitate debugging. This design approach resulted in the development of the Kerberos Control Unit, or KCU, a modular electronics backbone equipped with line-replaceable units. These LRUs can be hot-swapped even during operations in rough conditions. The standardized interface plate in the Kerberos electronics chassis can support up to 18 such modules, each supporting a specific data management, safety, or electromechanical function or system of the rover. Keeping parts replaceable like this decreases costs, both in the term of financial and mental health in the case of malfunction. The rocket boogie suspension system, alongside the double Ackerman steering, already proved itself reliable with ARTOS. And we kept this concept with Kerberos, making some improvements to suspension strength while reducing weight. A new feature is that the rover is now able to turn on the spot thanks to modifications to the suspension dimensions. Our 6 degrees of freedom robotic arm is mainly constructed from lightweight carbon fiber tubes and aluminium. It provides an interface to easily change the end effector to solve the probing and maintenance task. The rapidly exploring random tree algorithm serves as a global planner to compute collision-free end effector paths, whereas BioAK by the TAMS group is used to find optimal solutions for the inverse kinematic problem.
The drone for the ERC was contributed by us, the student group AKAMAV, also from the TU Braunschweig. We use a quadcopter with a weight of around 1 kilogram. The copter is equipped with a NVIDIA Jetson OWN, which runs the high-level mission control and also the marker and probe detection using a downward-facing camera. It communicates via MAV link with the flight controller and instructs its behavior. The companion computer software will be monitored and controlled by our own ground control program. The high-level mission control part and the marker detection are implemented in MATLAB. In contrast to the previous ERCs, we will not use GPS on our drone. The drone is designed to use visual odometry for localization using a stereo camera where the position is calculated on the Jetson and is fed into the flight controller. We use 2 ground stations. One of them with our own ground station software connects directly to the companion over Wi-Fi. It shows us the state of the drone and the state and progress of the mission. Additionally, we use a MAV link over Express LRS feature of the remote link to see the state of the drone and key ground control. A safety pilot with the remote control can enter land mode, take over control or stop the motors at any time using switches on the remote control. The remote controller also has switches to arm and disarm the drone and to change between the pilot controlled and autonomous mode.
We, the Drillbotics team at Clausthal University of Technology, are applying our expertise in drilling to design and build a new deep sampling device for Kerberos. Based on experimental results, we have chosen a vibration drilling mechanism due to its much simpler design compared to a percussive mechanism and its significantly higher efficiency compared to rotary drilling. That allowed us to design the system to reach a maximum depth of 400 millimeters. To ensure sample retention during extraction and transport, a new core catching mechanism is currently under testing. This feature prevents the sand sample from falling down from the drilling pipe during retraction or when the rover is moving.
The entire deep sampling device is mounted on a swivel mechanism, allowing it to fold horizontally on top of the rover when not in use. The configuration improves weight distribution, lowers the rover's center of mass, and preserves ground clearance while driving. The system is deployed to the front of the rover only when sampling is required.
This year, we're also introducing our new ground station Argo. This mobile unit contains everything we need to operate the rover, including a PC, 4 screens and a 5 GHz sector antenna. It also offers extra I/O ports for connecting additional computers and video sources. For odometry, this time around, we are utilizing the SAT stereo camera for our local pose estimation. The global pose is generated by the RTAP map SLAM algorithm and is updated if multiple Aruku markers are detected inside the camera frame. Until ERC, we're still planning to update the halo, replace the wheels with 6 identical models, and switch from our old SAT camera to our new Oak 4D Pro. We eagerly look forward to our participation in this year's European Rover Challenge to showcase the capabilities of our new Mars rover, Kerberos.